Okay, the doors have closed. You're all locked in here now. No escape from the ABI. Okay, I best make a start. So, hello, my name's Peter Smith. I'll be talking for hopefully about 50 minutes on the ABI. I've noticed there's a lack of a clock in here, so someone might have to give me a prod if I go on for too much in any particular time or anything like that.
Do you want the mark at 45 minutes?
Yeah, that would be helpful, thanks. So, best thing is if there's any questions at any point, please stop me and I'll go off and try and explain things as best I can. You'll be pleased to know I'm not going to be going through each of the individual documents in turn and reading lines of them out. That's probably not a good use of everyone's time. This is very much a sort of introduction to the ABI. I think probably best go to my agenda. That'll help me explain things a little bit better here. So basically where we're going to start from is where did the ABI come from? ARM didn't start off with an ABI. This sort of developed in about year 2003, and a little bit about the history where ARM was at that particular time. Then a sort of a little bit about the structure of the ABI. Many of you have noticed it doesn't look like the ABIs for many of the other processor architectures out there. Just give some of the reasons why it was structured the way it was structured. We'll then go on a little bit more about, okay, I as a user of the ABI, rather than how it was designed, what are my expectations of compatibility between, say, different object files, different libraries on an ARM system? And then we'll finish very, very quickly with a little bit about the 64-bit ABI and how it differs. So most of the time I'm going to be talking about the 32-bit ABI. A lot of you have noticed that the 64-bit ABI is much, much smaller than the 32-bit ABI, and it's very much more traditional. So I'll go on to the reasons for that later on. Okay, so a little bit about me. I'll go through this very, very quickly. So my background's with the ARM compiler, the ARM proprietary compiler toolchain from 2000 to 2016. I've gone through all the various names that the toolkit went through there, but if any of you are involved in the embedded systems area and have used ARM-CC, then you'll probably know the sort of toolkit that I've come from. My work's mostly been in what we call the minor tools in our in our team, or sometimes non-compiler tools, specifically ARM-Link, ARM-ASM, FromElf. And I'm currently looking at implementing ARM support in LLD as a Linaro assignee at the moment. So I wasn't involved in drafting of the original ABI, but I have been responsible for implementing a bit of it in the non-compiler tools. So that's mostly where my sort of experience comes from. Also the linkers, generally when ABI things start to collide and go wrong, then you get blamed for when two things aren't particularly compatible and you have to then go and find out what actually works out there. Okay, so we'll start off with some definitions because there's a lot of acronyms that get thrown around here. So I'm not going to go into these in any more detail. I'm just going to, or even argue about whether these are the best definitions. These are just the ones that I'm using. So ABI sounds very similar to API. So just, if anyone is not familiar with an ABI, is API very much an interface at source code level. ABI, now this is ABI in its traditional sense. Tends to mean an interface between an executable shared library and the operating system. That's slightly different to the ARM ABI, which whether this is actually an ARM term or PowerPC term, I think I may have seen it being used before as an embedded application binary interface, or EABI. So this is why you'll often see the term EABI rather than ABI, in that it's an interface between relocatable objects rather than an interface just between shared objects, executables, and the OS. By platform, what ARM tends to mean by that when it says a platform, it means something like Linux, BSD, Windows, Symbian. It means a rich platform with quite a lot of features that's able to independently load applications itself, and have a sort of rich set of features in itself. So the idea there is that if you were building an application executable for, say, Linux, you would have the expectation that the C library was a shared library on that system, whereas going to bare metal, which is our next definition, is you would expect that to be a statically linked executable. If it has an operating system, it will be an RTOS, and that RTOS will probably be statically linked as a library to the application. So when we say bare metal, we tend to mean something that isn't run on top of something like Linux or BSD, and it can or may or may not have an RTOS. If I say the word QOI, means quality of implementation, and that sort of means where in the ABI there will be various standards where you can say that you could conform to, but there are bits where you can say it is a quality of implementation definition whether you do more than what the ABI prescribes. And so, as we'll come to later, one of the sort of goals of the ABI was to allow different toolchain vendors to have quality of implementation differentiation in their toolkits. The idea of the ABI wasn't to stamp out vendors' abilities to improve their toolkits. Okay, so just a little bit about here what we're going to be talking about for the next few slides about what is an ABI. We'll go through what does an ABI define, why do I need to care about it at all, a little bit about ARM in the 2000s, which is where the ABI sort of was defined, and a bit about the motivations and principles behind the ABI. Okay, so here's a little bit of some points that I've put down for what does an ABI define. I've put the bits in black as the sorts of things that you probably think that you would have to do for a C and C++ ABI. The bits in blue are kind of, well, are they part of an ABI or not? Should that be something that ARM should be writing down in its documents about how these things should work? But typically what you'd be looking at is something like if you're going to call functions in two different object files, they need to be able to know the stack layouts, which parameters passed in registers, what the size is of the various things that you're passing. If you're going to throw an exception from one object to another, what's the exception format, that type of thing. If you're going to link two objects together, are they the same object file format? So these are sort of things that will come through there. Later on, you've got things like compiler helper functions. So to give you an example of a compiler helper function that was not part of the ABI, ARMCC has a function called something like common switch 8, which is part of an implementation of a switch statement, and it was for thumb in some cases. It was better to save code size to call out to a function that would then interpret a table. And that sort of thing is a sort of compiler helper function that you would need to have if you were to actually use the object file. So one of the things that you go to when you look for an ABI, to what degree can you standardize the sort of common set of compiler helper functions that get used across compilers? So again, that's a sort of one of those things where should that be part of the ABI or not? That's a sort of design decision for the ABI. Okay, so why should I actually care about all of this? Now, ideally you don't. If you're a user of these tools, everything should hopefully be abstracted away from you and everything should just work. You certainly should need to care if you're implementing a development tool of any sort of thing or any sort of kind of code generation. Certainly the sort of calling conventions if you're developing some kind of JIT or other sort of library-based things. It's also very useful if you're developing or distributing cross-platform binaries or cross-toolchain binaries, and you need to know what compatibility that you can expect, and also how to track down what's gone wrong when it doesn't quite work as it's expected. Okay. So we're going from now, okay, what is an ABI, to what were some of the motivations around the ABI when it first came through. So as I mentioned before, in early 2003, we didn't even have the IA64 ABI for C++. That was only just coming together at that time. So there's a lot of sort of standardization efforts all coming to fruition at this point. So there wasn't the sort of readily available things to jump on at that particular point. So what we had in the ARM ecosystem was a huge number of tool chains and RTOSes. One of the guys back at ARM had said there were upwards of 20 commercially available tool chains for ARM, each of it which had slightly different implementations of the procedure call standard, used different object file formats, different library formats, and one of the main problems the ABI was designed to solve was, okay, as an RTOS vendor, you had to ship about 20 different types of binary to be compatible with the 20 different types of development tool, and that was a huge sort of hindrance in the market at that particular point. But there were also differences in platforms as well. The ARM11 family had only just been released, and the ARM11 is kind of the first processor that could just about acceptably run Linux, I would think. There have been, there are some chips on the ARM9s that have run Linux, but I don't know quite how successful you would call those efforts were. As it mentions on the bottom slide there, the Consumer Electronics Linux Forum, or SELF, which I think has now merged into one of the other sort of Linux forums, was only just starting up in June 2003. So Linux was something that was thought as to be a strong future direction at this point, but the actual dominant mobile operating system was actually Symbian at that point. And if you were, pre-iPhone 2003, who was to say that Symbian might not have been here today at that particular point? So there was lots and lots of different. I guess you could say the whole market was much more fragmented than it is today. Okay, and here are some pictures of some things, some devices back from the day, including the Nokia Ngage, which I believe you held sideways, and it had one of the first internet memes of people walking around with side talking. A Palmos device, remember Palm, and then various sort of Symbian and Nokia S40 feature phones at that particular point. And I think you could say, even though I suppose you say a lot of ARM's revenue still comes from mobile, but I think more of it came from the mobile segment at that time than anything else. Okay, so starting from that mess, where do we go with the ABI? So at that particular point, in the IA64 C++ ABI was recently available and implemented in GCC and the commercially available EDG front end, which a lot of commercial compilers were using for their C++ front end. So you had a jumping on point for C++ at that point, where you could actually have a reasonable chance of compiling something on one C++ compiler and being able to link it against another object at that particular point. Linux was showing strong signs of being something big for the future, and Linux also had the advantage of coming with a lot of existing standards that if you wanted to run on Linux, you had to do it the Linux way. So anything that we wrote into the ABI had to support Linux in some way. And as I mentioned before, we needed to support the idea of RTOS vendors needing to reduce the amount of binary packages that they had to ship and test, whatever. So the idea here was to also encourage a market in binary objects. Now this sounds a bit weird for me talking about this in a sort of open source type conference. As it sort of turns out, the market for binary packages didn't really come together, and I think a lot of it's now, the market is now in source level compatibility, not binary compatibility. But back in 2003, we couldn't have predicted that. Now, notice the distinction here between enable independent binary packages. Now, this doesn't necessarily mean that the goal was that I can take any object compiled with any compiler and link it with any linker against any C library. That was thought of as a pipe dream, and it would, basically it would have been too difficult to get everyone to agree on all of the standards, and if we had, we would have killed all of the differentiation in the market. So the idea is that you would develop your binary package with an ABI compliant interface, but behind the interface you were free to sort of use any sort of nasty tricks that you wanted, as long as at the interface points you would then comply with that particular point. Okay, so here are the principles that I kind of went back through the sort of email trail to try and sort of find out from the original things. I say we probably have some of the original authors in the audience here who can correct me if I've got any of these wrong. But some of the things that you've got to look for when you're reading the ABI, first thing is that they don't stand alone. They will refer out to other documents. You have to interpret them with the architecture documents. So the ABI won't say what happens in every possible case. If, say, for example, you can work out what the correct one is by reading the ARM, it will build upon industry standards as much as possible. There's absolutely no point in ARM developing its own standards when there are existing industry standard ones available. One of the interesting points was that we were expecting platform owners where they said, okay, we've got this base level ARM-defined ABI. Now, ARM can't define the ABI for every possible operating system that could be built by any potential customer. So the idea was that ARM would define the neutral part that was common to all, or offer various sort of flavors of ABI for that then platform owners can then write their own documentation, basically saying, you must conform to the ARM ABI, and if you want to run your application on our platform, you need to conform to this additional ABI, which we will then publish ourselves. As it's turned out, platform owners are remarkably reluctant to write that type of documentation. So a lot of it tends to be, if it works, or it's defined by its implementation, not necessarily by any particular document. Yeah.
Any questions or comments so far?
There's a microphone here, and we can pass it around. If not, I'll carry on. Okay. So the conformance to the ABI follows what a lot of people in the compiler area would call the as-if rule, in that if no external observer can determine that you didn't conform, then you didn't need to conform. So at that particular point, yes, that type of thing. Toolchain vendors even can differentiate at a quality of implementation level, even at the extern interface. Now, when I say the extern interface, that's like the published interface of the binary package. Basically, this says, well, if a toolchain can say, oh, I can work out that all of the objects are from the same platform, therefore I can play all sorts of nasty tricks at link time because I know that all of the objects are from my toolchain, then that's still allowed. It's really, the idea is that if you want compatibility, you produce this interface, but it's not to stop anyone from going above and beyond that if they've got a very clever toolchain. Okay, and the final bit is where we had several existing toolchains with very strong views on certain options, and there would be no way of getting consensus among them. So a typical example of this is enum size. Some people were adamant that an enum should be the smallest possible size possible. This is very strong in the embedded sort of space where you need the smallest possible code size, whereas in the Linux area an enum is an int. There was no way you were going to get either one of those camps to change their existing behavior. So when you have two camps that won't change their behavior, you have to provide some kind of command line option to give a choice. And then you have to then provide some kind of option for tools to detect the incompatibility and then diagnose errors because of that choice. Okay. So we're out of the sort of motivation principles type thing, and we're now sort of onto how the documents are structured. So this is half of a document, half of a picture that's in one of the, I guess you call it the introduction to the ABI document you can download from the ARM website. I've got the other half on the next slide. When I put it all on one document, it was just a bit impossible to read. So this is the bottom half, and it's explaining the sort of contents of the ABI, and in terms of the documents and the actual underlying standards of which they're based. Obviously, I say they're cyan. Cyan has not come out as cyan here. It's come out as a very light green. But anyhow, So this is what we would call the base platform or base standards ABI. I'll go on to what the base platform ABI is on the next one, where that's where it interfaces with platforms. So you have this typical thing of AA ELF, ARM ELF builds on generic ELF, AA Dwarf built on top of the existing Dwarf. We have C++ ABI, procedure call standard, ARM's own exceptions ABI, a runtime ABI, and the runtime and CLib ABI are slightly different. The runtime ABI includes things like ABI, memcopy, that type of thing, whereas the C library ABI is a bit higher level than that. Okay, so at the top level, this is where things get slightly interesting, in that at the time the ABI was written, we had probably 4 different types of operating system that were likely to run on top of the ABI. Now, today, you could probably bring that down to 2. I'll let you guess which ones. But on the far left, you have the bare metal RTOS. That's where everything is statically linked. You don't have any dynamic linking going on. So that's generally the simplest possible thing for interface to an operating system, because the person defining all of those libraries in the RTOS is responsible for everything. Palmos at the time wanted to go for a shared library architecture, but only using or not using an MMU. So they had multiple processes, but would only use one address space. So that's one potential way you could write an operating system. Symbian, Symbian, I guess you could say, followed very much the Microsoft way of doing DLLs. So if you look at a Symbian DLL, they'll look very similar to a Microsoft PE or COF DLL. So that's a sort of, compared to a Linux-style shared library, the DLL is in some ways more efficient, it's more stripped down, but there are compromises because it's stripped down, and you have to do things like tell the compiler that you're importing with things like DLL import and DLL export, whereas the Linux shared library is very much down to, I want to minimize the distinction between somebody using a shared library and using a static library. And that's just 2 different design goals. But one of the strange things at the time is we thought that the embedded market for ARM was much more likely to go down the Symbian route because it was more efficient than the Linux route. As things have turned out, Symbian is now gone. Palmos, I think, turned into doing some kind of web JavaScript-based thing, then got bought out. And we're kind of left now with the RTOS, and we're left with Linux. And the sort of other ways of doing operating system-like things have gone. But the general idea at the ABI level was that we thought that if you could map your operating system dynamic loading type into one of those 4 families, you could abstract what the ABI needed to talk about down to supporting one of these 4 types, and you would then have post-processing going on at the platform level, which I'll go into later, to map your ABI compliant objects into what your platform would expect. Okay, so this is just a very simple showing how the ABI would expect to be layered with the different types of standards. So at the bottom you would have the industry standard. So ARM ELF is built upon the generic, or I think TIS stands for Tool Interface Standards ELF.
Actually, it's not. It was generic ELF from SCO.
Was it? Okay, right. I should say I don't
TIS ELF was a fork that we used in older ABIs.
Oh, okay. Oh, I've got that wrong. Sorry about that. So yes, the current home of the ABI is still the SCO website, although I don't know exactly what SCO is these days.
SCO has a website.
What's it? Yeah.
It's a shell these days.
Yes, but it's still where you find the document if you want to go for it. So ARM ELF is what contains, in ELF terms, the processor specific. So these are concepts specific to ARM's interpretation of ELF. So things like all the relocation directives, all the flags that live in the processor space, the platform-specific documents. These are things where you have concept specific to a platform's implementation of ELF. So, for example, dynamic linking on Linux, that's not an ARM concept. That is a Linux concept, or System 5 R4 concept, to be precise, I guess. So beyond ARM ELF, there is a sort of virtual document that represents the platform interpretation and rules on ELF. And typically that's written for an architecture in a System 5 R4 processor supplement, which doesn't actually exist for ARM, but I think it does for quite a lot of other architectures. So really you can see the ARM ABI as covering bits of what would normally go into the processor-specific supplement and other things as well, because it's an embedded ABI. Okay, so I'm not going to read all of that out. It's basically just a list of going through of what the actual documents are, what they do. As I mentioned before, generally the ABI for a particular architecture will be in the form of a System 5 process-specific supplement, but these sort of have been broken out into separate documents for the ARM ABI. Okay, so we're now going to move on from sort of the general structure to the ABI to relocatable object compatibility. So I've now got another document copied from one of the ABI docs, and it's a bit complicated to understand, so I'll be going through this a bit slowly. So as I mentioned before, there's no expectation that you can arbitrarily choose an object and compile it with any header, link it with any linker against any possible C library. There are some restrictions put in place, and this is what this document tries to come through. So looking here, we have you can see the difference in quotes between that and that and that. The header one is your applications library that will remain the same in both ways. You have one compiler tool chain here, another compiler tool chain here, and at the bottom we have both of these compilers must conform to whatever platform you're intending to run your executable on. But the general idea is that if you're using compiler 1, you have to use the header files that come with this runtime libraries that are with compiler 1. So these are things like, even within the ABI and potentially standard libraries like the C library, you may get differences in things like how they define var args, whatever. So the idea here, if this was ARMCC, you would use the ARMCC header files. If this was GCC, you'd use the GCC header files, for example. Once you've compiled your object, you both end up with an ELF file. Now, when I say here include private helpers, if we go back to the example I gave before of the ARM switch 8 thing, so that is not standardized. It's an ARMCC specific thing. So you couldn't expect to say link if the object didn't contain the implementation of switch 8, then you would either have to supply a library containing the definition of switch 8, or have that included within the object somehow. Otherwise, if you then try to link it with, say, GNU LD against the GNU libraries, then you would end up with that common switch 8 not being there. So one principle is that if there's a compiler-specific helper function that's not standardized, then it has to be contained within its own object. Or you supply a separate compiler header file to go with the link. So once we get down to here, we're now at the linker stage. So you could say that if this was the ARM compiler toolchain, ARM compiler 5, this would be ARM link. This was GCC. You would end up with GNU LD or Gold at this particular point. And the idea here is that you then have to you have to match the linker with the platform libraries that you're going to be using. So this would be ARM's implementation, binary libraries for the C library. If you used GNU LD, the only thing you could realistically expect to work would be something like newlib or glibc. You couldn't expect to take ARM's C library and put it on the command line with GNU's linker and expect it to work. The idea basically is the same as the headers here and the libraries here, is that toolchain manufacturers are expected or allowed to collude between the two here. So ARM's linker would understand special things that are in the ARM C library and could do special optimizations based on them. And the ABI wanted to preserve the ability of toolchain manufacturers to be able to basically collude between their linker and libraries and compiler and headers. So as we hear, the bit here is ABI functions. So these are the sort of compiler helper functions that are standardized across architectures. So these are things like neon intrinsics, that type of thing, where you want something that a bit of source code written here can have a realistic chance of running in both compilers. And then there's the normal C library, which would expect a compiler conforming to the C library to define. Okay.
A question.
Yeah.
So does that mean that you could potentially end up with as many copies of a private helper as you do objects in your final executable?
Generally no, because in ELF there's something called a COMDAT group. So there's basically technology in the ELF file that can allow the linker to compress all of that into one copy. So each object would have its own copy, but the linker would select just one of them at the final image time. So yeah, you would only end up with one at the final object. Okay, so this is a little bit about a QOI area. So one of the interesting things I mentioned early on about is enum size choice. So you'll find that GCC for Linux will default to enum is int. ARMCC for embedded will default to enum is the smallest possible size. Now obviously if you have an API function that takes an enum, if both of the compilers disagree, you could end up with a problem when at runtime. So there are things called build attributes that encode some of these ABI decisions in the object file, and the linker is able to give you a warning. So this is GNU LD's warning when it detects that someone has compiled with enum is int, enum is short, and you end up with a warning. Some linkers may give you an error in that particular case. But that's one thing that you can look for as one of the side effects of having an ABI where there is choice, is that you have to provide a mechanism to be able to detect errors. But the ABI doesn't require you to detect errors. This is a quality of implementation for a particular tool chain to be able to do things with the build attributes. Okay, so I mentioned before about the base platform ABI and how this was expected to work. So the bare metal case, which is also with including RTOS, you would produce ELF from the compiler, link it to produce an ELF executable. Now typically in an embedded system you don't run an ELF file directly. You would extract the binary bits and either burn them to flash or ROM or hex, something like that. And that's completely outside the scope of the ABI. Similarly at the bottom for a Linux style application where you're going to be executing the ELF file directly, you would just produce an ELF and link and produce a compatible file directly. For the DLL-like model or the Palm-OS-like model, it's obvious that unless you are going to expect a linker to be able to produce DLL, Microsoft PE, COF as well, or any custom file format that any sort of platform might have. In Symbian's case, they had one called E32, which wasn't ELF or COF or whatever. So it would be too much of a burden on the world's toolchain manufacturers to make them every linker support every possible object format that could potentially be done. So what we did was say, well, okay, we'll produce a superset of what can be done in an ELF file called a base platform ABI, XC or DLL, and this ELF file will contain enough information that somebody like Symbian could write a translator program and then produce their own custom object file format. So as far as I'm aware, Symbian are the only ones that ever did this. There's a program called ELF to E32, but again, Symbian's now pretty much ancient history. But this route here was what we expected a lot of the embedded industry to go down. We expected them to have a lot of their own custom object file formats for their platforms, but in the end it didn't materialize and most people just use Linux. So that's been a sort of a prediction that didn't come true. Okay, so I've gone through most of the sort of general structure. This is now just going to be a small number of slides of how do I find this damn ABI, because it's actually not as easy as it sounds to find. So the easiest way to find this is to go to infocenter.arm.com, which is this particular website here. There is another website called developer.arm.com that you can find the ABI on. When you do that, you have to type it into the search box. There isn't an easy way, a clickable way of getting to it. So the Info Center is currently the easiest way if you just want to click on ARM software development tools, and then it's the second entry down of the ABI for the ARM architecture, and you can get the PDF documents from there. Okay. So if you're a programmer, in an ideal world, you shouldn't have to go to the ABI unless things aren't working as they're supposed to do. So typically the ABI is a good point of call for diagnosing compatibility problems between this when you get those strange link errors and it'll say object X has build attribute Y and it clashes with some other ones. Well, the ABI can tell you what those clashes are, and then that gives you an opportunity to understand what's gone wrong. Certainly if you're trying to write assembly language and interface it to C, you'll need to look at the ABI to find out what the procedure call standard is, that type of thing. The addenda and errata in the ABI for the ARM architecture is a document that contains the build attributes information. And for the procedure call standard, obviously AAPCS. Okay, so some concluding thoughts about the ABI. So the world looks very different now to it does today, and it's certain that I think if ARM were going to try and introduce a 32-bit ABI now, it would probably look quite different to the one that we've got. There's a large amount of consolidation that's occurred. We've gone down from 20 available tool chains probably to about 5 or maybe 6, and a lot of them are now, well, all of them are now compliant to the ABI in some form or another, and GCC and Clang are very much aimed at the sort of Linux sort of style ABI. And there's also much more sharing going on at the source code level than there is at the object code level. There has not really been a sort of market for companies selling header files and binary objects. It seems to be that open source has killed a lot of that market. So now companies release source code, and you now build that source code with your own tool chain. So this sort of everything's sort of moved up a level to source code than back in sort of year 2000. And the problems of RTOS vendors having to ship 20 different binaries to 20 different tool chains doesn't exist anymore. Okay, so with that in mind, we sort of come to the sort of structure of the 64-bit ABI. So at this point, we had an opportunity to look at, well, do we just take the 32-bit ABI and add 64 bits to it? Or do we take a look at some of the decisions that we made and sort of try and simplify things? So you notice the 64-bit ABI is very much smaller. In many ways, it says less than the 32-bit ABI and is less prescriptive. And a lot of that's borne out by no matter what we write in the ABI, we can't force toolchain vendors to conform to it if they don't want to. Sharing has tended to be not at the mixing and matching individual objects. It tends to be, I build a shared library with compiler X, I build a whole library with compiler Y. I don't tend to mix in any particular applications. So it makes much more sense for 64-bit ABI, which is expected to run the software platforms. At the moment, there's very little sort of bare metal use of ART64. So we're really expecting the sort of unit of sharing to be at the Linux BSD type level than at the bottom. And we also find that the number of developers writing applications for a platform like Linux vastly outnumber the sort of OS and bare metal developers for ARC64. I don't think that's necessarily the case for ARC32, but that sort of just gives you an idea of why the ARC64 ABI is nowhere near as big as the ARC32 one. And we also find that because the ARC64 chips are so much more capable at the base level, we've not needed to do things like the custom exception table format, because we can just reuse the existing standards one as it is without worrying that it might be slightly less code size efficient. And that gives the advantages of faster development tools, because the closer we are to existing industry standards, the easier it is to implement. Okay, so the concluding thoughts from this is that the 32-bit ABI is an embedded ABI, and it's basically concentrating on the interoperability at the binary package level, not necessarily a mix and match of objects. Platforms can build their own standards on top of the ABI. So if you're introducing a new platform, you don't necessarily, and you need objects to do something, the idea isn't that you go back to ARM and say, I need you to rewrite the ABI so that you introduce the things for my platform. The idea is that you write a platform standard document that says, you want to run on my platform, this is what you need to do. At least that's the position from ARM at that particular point. 64-bit ABI is much more traditional, and it's concentrating on platforms rather than bare metal. Okay, so this is a general references slide, so if you do want to find out where to get these things from, here's the sort of general links to the various different documents. Again, won't read those out. It's there for anyone to look at if they want them. Okay, so that's all the material I had for here, so I'll be happy to try and answer any questions that I can. Or you're all desperate to get your lunch. If there are no more questions, then I can happy to leave it here.